Okay, so the next topic here is the antiderivatives in physics. So for this, we're going to look at just falling body problems. Okay, so falling body problems, all that means is that we're going to be, for instance, on a building, on top of a building, and then we're going to throw a ball upwards, and then gravity's going to take it, and then it's going to fall down. Okay, so basically the only acceleration that occurs is due to gravity. Okay, now if you remember, we discussed what the acceleration was due to gravity. If you recall, we said it was 9.8 meters per second squared. And remember, we got to worry about what's the positive direction and the negative direction. So what we're going to do here by convention, that this is the positive direction. Since gravity is pulling the ball closer to Earth, we got that it's going to be negative. And then we have that it also equals negative 32 feet per second squared, if we want to do it that way. And it's constant, it's not changing. Okay, so some other things that I wanted to mention was if we have v of t, if that's positive, then the ball is going upwards. If it's negative, then the ball is going downwards. Okay. We got s of t, if you remember, is the position function. And it's the height above the ground. Okay, now another thing that I wanted to point out was s of 0. What do you think s of 0 is? It is the initial position. At time 0, it's where you're starting to throw the ball. Initial position of ball. And then, similarly, we can look at v of 0. And that's going to be your initial, so at time 0, your initial velocity. So how far do you throw the ball? Or how, with what velocity do you throw the ball? Okay. There we are. If we also, one last thing, if you remember, we got a of t. The acceleration function equals the derivative of the velocity function and the second derivative of the position function. And that's going to help us here today. Okay, very nice. So for our first example, we're going to suppose an object is thrown upwards with a velocity of 16 feet per second. And then we're going to do it from a height of 32 feet above ground level. Okay, number 1, find the velocity. Okay, so if you could, A of t, acceleration due to gravity. We know that that's going to be negative 32 feet per second squared. We want to get to the velocity, and we know that the acceleration is the derivative of velocity. So we need to take the antiderivative to get to velocity. The antiderivative here, remember we got an imaginary x to the 0. Technically it's a t, because our variable is t. And so we got negative 32. And we add 1 to our exponent and then divide by the new exponent, and then we have plus c. So we got v of t equals negative 32t plus c. Now, question is, can we figure out what c is? And we can, because we're given some extra information. We're given that the velocity is thrown upwards at 16 feet per second. So that means we're throwing it, and so we have v of 0 equals 16 feet per second. Okay, so if we substitute in 0 here, we're going to get v of 0 equals negative 32 times 0 plus c. We substitute in, we know that v of 0 is 16. We get 32 times 0 is 0 plus c, and we get c equals 16. So that gives us that our velocity function equals negative 32t plus 16. And there we go. Part A is saying find the velocity. We definitely did that. Okay. Part B, find the position function. Alright, luckily, we already have the velocity function. So, and we know that the velocity function is the derivative of the position function. So we just had to take the antiderivative here. Okay, now there's one bit of information that we haven't used yet in our example, and it's this 32 feet above ground level. That's going to relate it to our initial position, which is 32. So we're going to have to use that here in a second. Alright, let's take the antiderivative here of the velocity function. So we have t to the first power, so the negative 32 is along for the ride. We add 1 to the exponent and then multiply by 1 over the new exponent, plus 16t, and then plus, I'm going to use c again here. And that equals our position function. Alright, let's clean it up here. So we got s of t equals negative 16. Negative 16t squared plus 16t plus c. And then we know s of 0 is 32. So we're going to substitute in 0. We get negative 16 times 0 squared plus 16 times 0 plus c. On the other hand, we know that S0 is 32, and we get that that equals 0 plus 0 equals c. So we get c equals 32 in this case. So in general, we have our position function equals negative 16t squared plus 16t plus 32. And there's our position function. Alright, so now part C is asking to find the maximum height. Alright, so if we were to draw this again, what's happening? So you're on a building. You have a ball, you're throwing it up, and then it goes back down. We want to figure out where this max height is. What's the maximum height? So it's the height here, so S of t. We want to know what that is. We can figure out where the height is when the velocity is 0. So keep in mind our velocity is going up and then it's going down once we're after the peak. So right there at the peak, we're going to have our velocity is 0. In other words, we get a horizontal tangent line, and so we can find the time of when the velocity is 0, and then substitute that into our position function. So first of all, we're going to find the time. When the velocity is 0. Okay, so we're going to look at v of t and set it equal to 0. Subtract 16 on both sides. Or how about we add 32 on both sides? That's nicer. 32t, divide by 32. We get t equals 1/2. There we go. That's the time when it reaches the max height. But then we want to know the max height. So we're going to substitute that into the position function. So we got S of t. We're going to substitute in 1/2. Okay, so 1/2 squared is 1/4. We got 16 divided by 4 is 4. And then we have plus 8 plus 32. We get 40 minus 4 is 36. So we get 36 feet is the max height. All right. Now, believe it or not, we got a part D.